to chapter 2, which is series of groups. We have seen series of groups last semester, but I will repeat some and we continue with group actions on the set. Okay. What happened to the one you're supposed to get your book? I think, I'm not sure. Vian, you got it, right?
Yes, Prof, I got.
Okay. By post is one day. Okay, so series of groups. You still remember? It's just last semester. Lava, you still remember? Series of groups?
Yes, Prof.
Okay, so this is a little bit of reviewing because we are studying the structure of groups. Okay, now we also see if we have one group and the subgroups, and we can see the structure of the groups by its subgroups. Okay, and we define a group series, a series of groups. So the first one is called subnormal series. Subnormal series. So we let G be a group. So we have to have a series of subgroups. And H1, do I need to start with H0, H1, H2 until Hn, subgroups of G. Okay, you probably have not that many, but suppose G is a group, G have this series of finite sequence of subgroups. Finite. You don't want until ... Okay? And we have this condition. We want Hi to be normal in Hi plus 1. So it has to be a sequence, and Hi has to be a subgroup of Hi plus 1. One is supposed to be smaller than the other one. You cannot just take one subgroup but not connected. You remember last time we draw this? You remember, right? And then we have 2 and 3, right? And then we have 6, and then we have 4. Right? We have this. Remember? So you cannot take this and this because they don't contain in the other one. This is subgroup, but you cannot take together in one series, right? It has to be a subgroup. So these are subgroups, but one has to be normal in the other one. Okay, and not just that, we want the first one to be the trivial subgroup. Okay, and the last one is the whole group. Okay, then H0, H1, H2 until Hn is called a subnormal series of okay. So the definition is there is a normal. So you have to check whether one is normal to the next one. I'm not saying that HI has to be normal in G. That is the next definition. The next definition is normal series. Okay, so definition 2.2 is normal series in which it is normal to the whole group. Right? So in this case, as one example, for this one, since G is Z12, abelian, right? Z12 is abelian, so all subgroups are normal. Okay, you have to remember this. For abelian groups, all subgroups are normal by definition. So you don't have to check the normality of the subgroups. So find me one series, one subnormal series. In this case, it's normal series also, but since we are defining subnormal, we say subnormal for now. Someone, can you volunteer and give me a series from this? You have to give me what is all this. Okay, who want to try?
0 sub 6 and Z 6 subnormal 6 Z 12.
Okay, so this is one series because starts with this, end with this, and there is one in the middle in which this is normal to this. See, because Z12 is abelian. Yeah. Okay, I need another volunteer to give me one other series, another series, subnormal series. You want to try?
0.
Okay, Vian, you want to try?
Yes, Prof. 0
Mm-hmm.
subnormal of 6.
Oh,
6.
6. Okay.
Yes, subnormal of 2.
2. Okay.
Yes, subnormal for
Normal
Z12. Z12.
Okay. I think each one can give one, right? Let's try if each one can give one. Hannah, your turn. Hannah?
4
Or
Z12.
Z12. Okay?
Yes.
Okay. Shiham. 6. That's 6 Z12. 3. Z12. Okay. Lava? Use this.
0, 4,
4.
2, 12.
Hmm?
2, 2,
2.
12.
Z. So we have covered 0, 6, Z. 0, 6, 2, Z. 0, 4, Z. 0, 4, 2, Z. 0, 6, 3, Z. 0, 4, 2, Z. Anything else? Covered? I think we have covered, right? Because from 06 direct, 06 to 063. And then from 404 direct, 042. There's one more. There's one more. Farah?
03 Zactal.
03
Zactal.
Okay, one more. Fozia. Like this.
02 Z12.
Whose name I didn't call yet. I already. Okay. Any more? The easiest one, Ain.
0 and Z2, Z12.
Okay. 0. That's without all this. That's the trivial one, right? So you see, it's very easy to list when you got the subgroup lattice, right? Subgroup lattice. Okay, let's try one more. Okay, let's draw the subgroup lattice of dihedral group. We have D4, right? Okay, everyone. You can write the elements of D4. Don't wait for me. And write the subgroup lattice. So I use rotation. H, V, D, D4. Then order 8 and not secret, right? Because elements order 1, 4, 2, 4, 2, 2, 2, 2. So there is no element of order 8. There is no generator. So D4 is not secret. Okay, it's also not abelian because not commute, right? Okay, so we have subgroups of order 1, 2, 4. Okay, try and list all subgroups under a subgroup lattice. So you have D4, and then you have a subgroup of rotation, which is also secret, generated by R90. If you don't remember, take out your group theory 1 or modern algebra or abstract algebra. This is order 4. Then you have order 2, right? And then you have this. So this is the the rotation, the series of rotation. Okay. Next, we have also a subgroup of order 4, which is not cyclic. Okay, which is isomorphic to, if you have H is order 4, H not cyclic. So H is isomorphic to Klein 4 group, right? Klein 4 group, in which elements are all of order 1 and order 2. Okay, this is Klein. Okay, so if you remember still, we have, this is actually element in the center. R180 is element in the center, right? It's the center. D prime, right? Okay. And then I think this is a question last semester in the final. H, B, right? Okay. Okay. That's the only subgroups of order 4. Now, there's also subgroups of order 2, which is cyclic. Remember, a group of order prime P is cyclic. This is prime, right? You remember you had to prove that. So you have proved that. Okay, so under this is connected to all, right? Right? Because R180 is R0 and R180. But also we have D and D prime. Right? So this, we also have H and D, right? And all has, is that right? Okay, so this is a subgroup lattice of dihedral group of order 8. Okay, can you see now the subnormal series? Okay, can you give one? Volunteer? Let me give you a hint. Okay, subnormal series. What's the hint? It starts with R0. It ends with D4. Okay, fill in the blank. Wali. Are you here? Ding. Time's up. Vian.
Yes, Prof.
Can you give me one subnormal series?
Yes. R not. Yes. R 180. R 90.
R90. Right? Okay. Fauzia, give me another one.
are not normal about HV.
H. Then
Normal about R not
one
R
this one
HV.
I call it K1,
Okay.
K2, K3.
K3. Normal about K3.
K3,
Normal D4.
okay. Okay. Farah. Can you give one, Farah? Unmute.
Not ready,
Farah?
Prof. Not
Yeah?
ready, Prof.
Just take one like this. There's so many.
Are
Just take one like
not
this.
V
You can use V, right?
K3 D4.
Okay. Okay. Because, right? Then two more. Right? With the length 4, right? Length 3 actually. Length 3. Okay, so you have 1, 2. Oh, 1, 2, 3, 4, 5, 6, 7. Length 3. Because you also have this. 1, 2, 3, 4, 5, 6, 7. Okay. Okay, that is length 3. 7 subnormal series. Length 3 is 1, 2, 3. Okay, now not a subnormal series. Can you give me not subnormal series? Want to try? You have to start with R0 and with D. Who want to try?
Or not? I want to try, Prof. Or not? H,
H.
yes, K1 and D4.
H. K1. Cannot
Yes.
do K1. K1 cannot. Cannot do K1 because K1 is H is not under K1. So it's not even a subgroup. You remember you have to have a subgroup in the subsequent series. Try again, Hassan.
It's not normal?
Hmm?
Normal or not normal?
Not a subnormal series.
Not a subnormal.
It's a series, but it is not subnormal.
H, K3, D4.
H and next
Next, K3, D4.
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 Okay.
Oh, yes. Yes.
This is of order 2, and this is not normal to D4.
Hmm.
It's not normal. Okay,
Yes.
you can show that. So it is not a subnormal series. It is a subgroup. Now my next question. There are many, right? All this. These are not But yes, right?
But only the element of the center, yes. Yeah.
This is yes. Because this is the center. Center is normal. Okay. This is not normal. Okay. If you have any question, just ask. Why is it all normal? How do I know? Because all of this is order 1, order 2, order 4, order 8. And the index is 2. Right? The index is 2, the index is 2, the index is 2. So that's why. Now I'm hot. Okay, so this is one example. Now, next example is normal series. I'm not going to erase because I want to use this again. I hope there's a more whiteboard because I don't want to erase Z12. But in Z12, it's a billion. So all the subgroups are normal to the next one and normal to the whole group. Okay, I will write the next definition. Maybe I can use this one. The definition before change. What's the definition before? The definition before said subnormal series, yeah? Remember this? Okay, this is the definition of subnormal series. Now, for normal series, you have to have it's normal to the whole group. Okay, that's the difference, right? So, to see whether this is normal series or not, you cannot erase yours, I can erase mine. You have to copy paste your previous example. Okay, so not only you see this is normal to the next one, you have to see whether this is normal to the whole group. Okay, so for this one is yes, because this is normal, it's the center. This, no, because this one is not normal to this one. Okay, it has to be normal to the whole one. This, no. Okay, so normal series, we have only the layers subgroup lattice, the layers with the K, right? So you have okay, done. Okay, so how many? We have just now. This one, okay. This one is of length 1, 2, 3. Okay. Now, this one is of length 2, right? So I already get that. And next one is what? I call it K, right? K, right? The other one is K what? K? K2. 3. K3. This is I call it K2. This I call it K2, right? R90 is K2? Oh, So I still have that, right? Okay. Oh, okay. So this I erase. R90, yeah? R90 is the one I used to. Right? Because the index is 2. That's easy. The index is 2. So if you are not sure how to determine whether subgroup is normal or not, you have to go back the previous notes, like what is a normal subgroup. Okay, I would expect you to know whether a subgroup is normal or not in all kind of groups that we have learned so far. Quaternion, dihedral, symmetric, and so forth. Okay. Right. Okay. Done subnormal. Done normal. Okay. If it's abelian group, then it's okay. All subgroups, all those series, if they are in a series sequence, then they are all subnormal and also normal for abelian, right? If it is not abelian, then you really have to check. Okay, so theorem 2.1, every normal series is also subnormal, right? Because it satisfy more than it should be for normal, right? Okay. I also mentioned already theorem 2.2, if you have abelian groups, so they have both subnormal and normal series. There are groups probably don't have a normal series in which the one in the middle is proper. Sometimes they only have the trivial and itself, if they don't have something in the middle, right? All simple groups, they don't have anything normal in the middle. So you cannot have the improper, the not proper one. The simple groups have nothing in between. So simple groups only have, for simple groups, right? So for simple groups, you only have this. Okay. Now this one is new. This one was not in the last semester. Okay. Refinement of series. Refinement of series. Okay. Now a refinement of series meaning you already have a series, and then you want a refinement of that series, meaning you want something to cover or contains more, bigger, like covering, right? But covering subgroups is different. So let me just give the definition. Okay. So a refinement of a subnormal series. Why is it a refinement of subnormal series? Again, let G be a group, and you have two series, okay? HI and why is KI or KJ? KJ are two subnormal series of. Just now we had many, right? So just pick two. Okay, then the series KJ is a refinement of a subnormal series HI of G. So I assume that K is bigger if this is contained subsets of this. Okay, meaning HI is one of the K. What does it mean? Just now, you have shorter one, you have longer one, right? You have this. Oops, let me use generated by. This is the shorter one. What's the longer one? There are three things on top, right? You remember the subgroup lattice, the one that contains R180. You can put either K1, right? You can put either K1, K2, or K3, right? So I put Ki. So this is called the refinement of this, because this is in here, this is in here, this is in here, but you have extra. Ki has extra. Okay, so this is called refinement. And you have many others in the example just now, but you have to have a starting with subnormal series. Okay, even for Z just now, right? We can do the shorter one. What is it just now? 6, right? And bigger one, 6, 2, right? And or 3. Okay, and many others. You see, if you draw the subgroup lattice, it's really clear, right? Which one is refinement of shorter one, longer one. Okay, so that's refinement. And also a refinement of normal series. Okay, some of the subnormal, they are not normal. So you can change the definition of refinement of normal series. Okay, so definition 2.4. So still you have G is a group, HI and KJ are normal series. Typo. Normal series. Okay, normal series. Then the series KI is a refinement of a normal series HI. Again, the same. The difference is that just that this one we want the normal. So this is okay, right? This is okay. This is also okay because I choose the normal one. Even this one is a normal one. There's a difference if the original one is subnormal but not normal, right? The one that I put here, not normal. Erase. Okay. Next is central series. I think you still remember this. You've seen this last time. Central series. Okay, central series. Okay, a central series is a normal series. Okay, a central series is a normal series. is a normal series. Okay, so I choose a different symbol here, maybe just so that it's not similar to the one before. Okay, so our series always start with the trivial one, ends with G, where each successive quotient is central. So AI plus 1 of AI, the quotient series is central, is in the center of G mod AI. Okay, this is the center of the factor group. Why we need it as normal? Because factor group, if you remember, we learned this before, factor group is only defined if H is normal, right? That's the condition. To define a factor group, G mod H, H has to be normal in the first place. That is why you need a normal series. Okay, what is this? You have to check in each of this mod this, is it a subgroup of, a subgroup of the center of this. You have to check. Okay, let's look at one example. Okay, now normally I will write like this, and this is called the upper central series. If I go the other way around, this will be called the lower central series. You just write the other way around, like right? I'm not used to writing this here. That way, right? This is lower central series, but I normally use the upper central series, not lower. Okay, now if you have this series, E, stop Hn to be G, then the series has length n. Okay, so but you start with 0, so it's 1 here, 2 here, until n here, right? Like if you have this is 1, 2. Okay, we count this one, length 2, and this will lead to the definition of nilpotent group. Nilpotent group and nilpotency class. Okay. A group G is said to be nilpotent if its central series is of finite length. Okay, as long as you have a finite length of this central series, then the group G is nilpotent. Okay, and the shortest length, why there is a word shortest? Because they might be longer, right? Just now we have seen many series of length 2, of length 3, of length 4. So the shortest one is the null pointer class, right? So this is a group of null pointer class N. If you look at dihedral, right? Let's look at dihedral. Or before that, there's an example here. S3. What about a billion group? Is a billion group null pointer? Anyone want to answer? If you can find a series, suppose you have a group G, right? If you want the shortest one, that will be this, right? The shortest. Okay, now, yes, this is normal in here. It's a normal series. What about G mod E? Is it a subgroup of the center of the same thing? There's nothing else in the middle. G mod E is isomorphic to G. G mod out the trivial subgroup is always isomorphic to G. Now, this is isomorphic to G. What is the center of G? If G is a billion?
Identity.
The center of G when G is a billion? It's G. Yes, G, this is G, right? So this is okay. So this is a central series. And this is the shortest central series. There's no more shorter. There's no more shorter. You have to start with this, you have to end with this. So, yes, of class 1. Okay. All right, let's try with the non-abelian one. What's the smallest non-abelian group? I asked in the first class. S3. Okay, let's see. Okay, now draw the subgroup lattice of S3. 1. Okay. Draw the subgroup lattice of S3. Let me have my coffee. So S3 is of order 6, meaning the subgroup has to have order 2 and 3. All right, so you have S3, and then you have subgroup of order 3, right? How many subgroups of order 2? 3. I put it down here because they have smaller order. Right? 1, 2, 3, 4, 5, 6. Okay. All right. So how many normal subgroups does S3 have? How many? How many normal subgroups? Does
One.
S3 only?
1, 2, 3.
Only this is normal in S3. Only one. Okay. So with this, then you know that you cannot have normal series that include this, right? Because if you have a series that include this, is not normal, you won't have a normal series. For example, you cannot say this is a normal series, right? This is not a normal series because this is not normal. Okay, so this is a series, but it's not normal. It is also not a subnormal series, right? Not normal, not subnormal. Okay, if you have only length 2, subnormal and normal is the same thing, right? If the length is 2, then normal is equal to subnormal series. Because you don't have something in the middle. Okay, okay, so you only have one normal series. This, which is also subnormal series. Right? Okay, now you want to see, since you only have one, you want to check. Suppose I have this. Normal series, right? Okay. This is a normal series. Only one. Also subnormal. So we want to check the central series, right? So a central series has to be normal first. Then you can check whether it's a central series or not. Okay. If this is a central series, meaning the length is 2 and it's nilpotent of plus 2. But we have to check. Now, how do you check? So you have to check S3 mod 1, 2, 3. Is it a subgroup of the center, right? S3 mod 1, 2, 3. Now, S3 mod 1, 2, 3, what is it? This is of order 6. This is of order 3. 6 over 3 is 2. So this is isomorphic to Z2. Because any group of order 2 is cyclic. Any cyclic group is isomorphic to Z or Z2. That's chapter 3 last. Okay, now what is this? Oh, here. Okay. This is center of Z2. What is the center of Z2? A billion, right? Z2 is a billion, the center is Z2. So this is okay. This is okay. Okay. But this is not the shortest, right? What about this? Okay. So why I said there that symmetric group is not nilpotent of class 1 or any others? Otherwise, can I say that all are nilpotent class 1? That's the reason that I don't want to give the answer now. Okay, that's a simple exercise for you for next class. I don't want to continue until the end. Okay, find the upper central series of Q and D8. Next class is Wednesday. Wednesday that you have an assignment due, so please upload in the e-learning. Make sure you upload the cover. Yeah, the assignment has a cover, and upload together with the cover, so I can put in the marks. Okay, but find the upper central series of quaternion and dihedral. I have done some series, so you take one normal series and then check this. You try first. If you have question on how I get this, I can explain in detail, but you try and see how and why. Right? On Wednesday, I will start with the next series. So you have to read through for next class, isomorphic series, composition series, and review. I have done this before. Solvable groups. Okay, so our class next time will be 2 to 4. Okay, 2 to 4 as usual. Because today I had like a long series of lectures. And then I will start with the action, group action. But this is just a short one, just to introduce what is a group action on a set, what is an orbit, and so many research use this facts. So at least you know some of this. All right? Any question?
Sorry, Prof, for the trivial subgroup. Every
Yes.
trivial subgroup is normal in the group. So if we consider the nilpotency of class 1, every group is
That's what.
nilpotent of class 1. So
That is exactly what I said just now. Why we cannot take every time that everything is nilpotent of class 1. Okay, Hassan,
So-
you understand
so
my
if-
question?
in this case, S3 is the nilpotency of class 2, yeah?
That is my next question. Okay, why I put it 1 and not 2? Okay, I will give the answer in the next class.
Okay.
I didn't say yes, that's, but why did I put that? Or maybe it's a typo or what? Find the
Okay.
answer and we will discuss in the next class. Okay.
I think for the previous semester that we learned from the group theory 1 that the length of the class is the nilpotency. If the group is a series of length 2, then its class of lin 2 is an input in class of
2.
2. Yeah, if it's 3, then it's 3.
Yep. I erase this, so the potency class is the length of the central series.
Yeah, upper.
So that's the 2 questions that I will start next class with, right?
Okay.
Why we cannot put for all groups, this is the shortest one. If this is the shortest one, which is true, then all groups is of class 1. My next sentence will give the answer. I don't want to give the answer. But why then the header group has class 2, not 1? Okay, that's the answer for that. Hassan, you understand?
Okay.
In the next class, I will explain why we cannot choose this at all time. Although this is true in the sense that this is the shortest one, right? And then if I say it again, then I will give you the answer. One of it is try this, right? If this is not a billion, this not this, is this? Is it in the center of this? If it's not a billion, it's not the whole group. See, Hassan, you make me give the answer. Next class, we'll explain. Okay, any other question by not asking the thing that I asked you to think? Until next class. No? Okay? I think it's clear, right? The subnormal series and the normal series.